All right. Hello, everyone. Hello. Hello, hello, hello. People. If nobody wants to study today. All right. Can you hear me in the back? All right. Any questions from last time? None? All right. Let's still look at what we saw last time, but with a different lens. So we looked at feed-forward networks or multi-layer perceptrons. So you get an input x. So in this case, say it's a vector of size 4. So m here is 4. And you want to generate an output of size 3. So yes?
Will we be uploading these slides and we have to send Monday's slides somewhere?
Sure, I can do that, yeah.
They're not the same as the ones on the website.
Okay. All right, yeah, do that. All right, so we want to get some output of, say, size 3. We come up with this feed-forward network, which has 2 hidden layers. So one thing, okay, let's call them H1s and H2s. One thing we didn't really nail down last time is that you can write one of these hidden layer outputs as a matrix vector multiplication. Is that obvious? Does anybody, okay, it's already there. Can anybody justify the size of W1 here? Someone? Great question. What is W1? What do you think it is? These are the weight vectors, yes. So these are written as a matrix. Can you try to tell us what the elements of this matrix are? What are the parameters? Sorry? 3.
4 cross
6 cross 4. D1 is 6, for example, in this case, right? And M is 4. So, okay, it's a 6 cross 4 matrix where, say, the first row of size 4 are these 4 vectors that correspond to the connections between x1, x2, x3, and x4 with the first hidden unit or the first layer. Does this, again, look similar to a linear threshold unit that you guys have been looking at? So in the last class, we established, right, that a single hidden layer is basically these parallel stackings of linear threshold units, but with a non-linear activation. right? Okay. And similarly, any column of this matrix will correspond to the weights from one of these inputs to all the connections, all the neurons in the hidden layer. Is this clear? Is this other questions here? Because this is quite important. I still see a lot of blank spaces, so just ask if you don't understand. Okay, so can anybody tell us what the parameters for the next connections would look like? For the next hidden layer? Or what the size of that matrix would be? 5 by 6. So that's D2 cross D1, right? And similarly, the last layer would be N cross D2. I have taken away the bias parameters here or the threshold parameters here, but yes, they are there. So this also tells you how many parameters there are in this model. Anyone? Yes?
You just add the matrices, so D1 plus N plus D2 plus D1 plus N plus D2 elements.
Right. Is that obvious? Is that clear? So the W's are the only parameters in this model right now. So this is all that you have to learn in order to learn this architecture. And someone in the last class mentioned that these are non-linear functions because we are stacking up layers. Can anyone tell us why that is not true? That non-linearity doesn't come from stacking up layers. Is it? Can anyone look at this and now explain us why?
Composition of linear units.
In simpler words? Oh, come on, you cannot simplify it. What does composition of linear units mean?
Like the output of one layer is again given to a linear unit and it propagates like that. So if the sigmoid was not there, it would always be linear.
Okay, let's simplify that down even further. So okay, so actually there's a typo in this in this slide. So H1 is equal to sigma of W1x, not W1x. But for example, if that were the case, if H1 was equal to W1x, so forget all these sigmas there, all those functions there. What would H2 be in that case? Could anybody tell us? Sorry? No, H2. W2 times W1 times X. So you can write W2 times W1 as some other matrix, right? So it would again become a linear function, and you can keep doing that. So your final output Y, in that case, could be written up as a multiplication of different matrices and some input. So that would still lead to a linear function, right? Is that clear? Anybody has reservations? Is there? No. Okay. So we don't get non-linearity by just stacking up layers. These sigmoid functions are what cause non-linearity. Okay. Quick note at the back propagation algorithm that we saw last time. So how you would do this is, suppose you have a network like this, you would initialize those three matrices, W1, W2, W3, with some random weights. You get a bunch of training data, which is written as xi, ti tuples. You will take one of those data points, xi being the input, ti being the truth you're looking for. You would compute the error, or you would first do a forward pass, get the yi, compute the error, then compute the gradients for all parameters. This is, again, you would get gradients for all these matrices, basically all elements inside these matrices. And then you will make a small step in the negative direction. There's again a typo here. That should be negative wij minus r gradient. Any questions? Okay. Anyway, we saw a lot of math last class, but sorry, I didn't see. Oh.
On the previous slide,
Mm-hmm.
so when you're representing, say, the input layer to the hidden layer
Right.
of the matrix, so for example, the value in the second row and third column would be like the weight vector from x2 to like f3.
Mm-hmm. Yes. Oh, yes. Yeah. Is that clear? So maybe this would help. So the first row has 4 elements in it, which correspond to connections from x1, x2, x3, and x4 to whatever h11 is, right? And similarly, the columns are these. Okay. Great. We saw a lot of math last class, but you don't really need it in practice. There are these auto-diff packages, auto-differentiation packages. Has anybody heard of them? Torch, PyTorch, TensorFlow, there was Theano, some point, Chainer, there's tons of them that do all of this for you. So what you need to come up with is an architecture like this, some data, and it will give you the gradients given some loss function. Can quickly try to show you. Is this readable? Okay. Yes, sure. This? All right, great. So let's do this. I'm showing just one input here, x, which is of size what? It's a 4 size vector. Then what I do is I make one hidden layer, which goes from 4 elements to 16 elements, right? So how many parameters are there in this linear layer or this hidden layer? Sorry? You said 16? The parameters in the matrix, so 16 times 4, yes. The size of the hidden layer or the hidden representation is 16, but the parameters you have to learn is 4 times 16. Okay. Similarly, what I do is I stack up another layer, which is 16 times 6, or goes from 16 hidden neurons to 6, and then goes from 6 to 2. All right? So my output is of size 2, right? The y in the slides we saw, and I define some gold, which is the ti, which is of size 2, some data point. So basically, what you're getting as training data is this x, the 1, 0, 1, 1, and the gold, which is 1 and 0. Okay? All right. I do a forward pass here. So I say my h1 is there's this h1 layer that I had, and you compose it with this input x. So basically compute whatever the w1x is, and also the sigmoid function on top of it. Is that clear? Yes, question.
In the 11th line, to the SGD, you're giving just the parameters of L3 as input. So does that even include the parameters of x2 and h1, or do you need to give them explicitly?
Which line? Forget it. It's not there. So H1. Any questions here? Yes.
Sorry, could you just explain again what gold is?
Gold is the TI over here. So what you're trying to learn is this function that takes a vector of size 4 as input and outputs a vector of size 2, right? So given, given,
That's essentially like the correct output.
yes, that is the goal. So I don't know, in machine learning, it is usually called the goal truth, hence.
And what does the tensor function do?
It's something to do with the PyTorch package. It converts it into basically a vector that this package understands. Otherwise, it would just be a Python list, right? Okay. Don't worry about the specifics of the package. Just try to get an idea of the overall architecture we're after. Okay. So no questions in this line. So then, what is the size of h1 over here? 16. It's a vector of size 16. Right. Similarly, what I do is I take h1, pass it through the h2 layer, and get a vector h2 of size 6. And similarly, y is by inputting h2 into this h3 layer. Great. I define some optimizer. Yes, I have cheated here. I've only given h3 as parameters. But what you give is some kind of a learning rate, the capital R we saw here, right? Okay, great. And I also compute the loss, which is the E function over here. So what I'm doing is I'm computing the square of y minus gold. So that's the tki minus oki whole squared. And I'm doing a sum over the 2 dimensions. Anyway, loss is some scalar function that I want to minimize. Great. Okay, let's look at this. This is also not readable, I assume. Or is this okay?
Can you make it bigger?
I can try to. This works. Okay. This works? Better? This? Okay. So I was just doing a take. So you see the goal that we input is printing that. Then what I print is the size of h1, which was 16. As you guys said, h2 was 6. This is the output from the model of size 2, which is very far from the goal, which is 1, 0. So what we should get is a non-zero loss value, right? Okay. Okay. Just a quick check again. How many parameters are there in this H3 layer, the final layer? For reference, 6 by 2. And also there are two bias parameters, the 2 threshold parameters. So it's basically a matrix of size 6 by 2 and a vector of size 2. So this is what it is. So the parameter values before the update for H3 is this matrix of size 6 cross 2, and some bias vector of size 2. By the way, when we got this output y, we had already done the forward pass, right? Great. Okay. Now I call this function loss.backward, which is basically computing the gradients for you. That is doing the whole backward pass and computing the gradients across the layers. Something happens, and these are the gradients I get. Okay? So obviously, for each parameter, you should have a gradient value, right? So the size of the gradient is the same as the parameters. I'm only showing this for the H3 layer. Okay, let's look at the first bias term over here. So the value is negative 0.12. The gradient we compute is negative 1.7. So after the update, should this value go up or should it go down? Sorry? Up. And why is that?
Subtract the gradient into R.
Right. So we in gradient descent, we move in the negative direction of the gradient. So if the gradient is negative, you would be adding something positive to this value, right? So that is what we see. So we go from negative 0.1 to negative 0.03, right? And you can kind of verify that for the other parameters. But all that math we did is not really necessary for you to, like, you don't have to do it by hand. You will get packages like these, and you have successfully done one step of the backprop algorithm. In practice, what you would have is tons of xi and gold data like this, and you would do this in a loop. You would just iterate over your data and keep doing these processes. Okay, any questions? None? All right. We looked at dropout last time, but in a hurry. Let's look at it again in a hurry. Okay, so last time we kind of established that what these neural networks or these feed-forward networks lead to is over-parameterization sometimes. Can anybody tell us what that means? What does over-parameterization mean?
Maybe so many weights are not required to most of them become.
Yes and no. So yes, it is true that you don't know how many parameters you actually need to model this data. So you might end up with a model which has more parameters, which leads to more expressivity of the model, and it might lead to overfitting. Basically, you start modeling noise in the training data, and you stop generalizing, right? Doesn't really mean that those weights will go to 0. Those will actually create a havoc. So dropout was, okay, so what do you do when your machine learning model starts overfitting?
Like pruning a tree or something.
Yes, there is a generic blanket name for this.
I don't know the name, but I was going to say just you try and remove expressivity in a way that doesn't affect your testing accuracy.
Yes, exactly. So yes, regularization. So regularization precisely is you try to limit the expressivity of your model somehow and still see that you get the same kind of train test performance. So there are multiple ways to regularize. In decision trees, you've seen you can prune trees, right? In perceptron, what did you do to regularize? Sorry?
We took norm of W and minimized it.
Right, so you added a term in your loss function where you try to minimize the norm of W, right? So that is, so if you take the two norm, it is called L2 regularization, very commonly used. People tried that for neural networks, but it didn't really help as much. So there was this technique called dropout training, introduced in 2012, very widely used. Basically, it is used in all networks that you would see around. And the idea is that while training, you don't use the full network. You randomly sample some hidden nodes, and you don't use them at all. So suppose you have a single hidden layer with 7 units. You randomly sample 3 of them, and you say that I will not use them in my training. And the idea is, there are speculations for ideas of what is exactly happening, but one is that you don't let the weight vectors become very high, or you don't let the model over-depend on some neurons, and you try to distribute computations across the network. Do you get an intuition of what is happening? Yes, question.
Is this for each epoch, or is it for each like training sample? Like, how often do we change this node?
Good question. So you do this at every step. So when you take an input gold pair, and when you're doing the forward pass, you would first sample neurons to not use, then do the forward pass, do the backward pass, and then you get another training sample. You would randomly draw a sample again. It's every time.
Different each training sample.
Yes. so if, yes?
We'll go to the previous slide. So as you said, we do not exactly know how many parameters we need to model a given problem. So it's clear that if we're using more parameters than we actually needed, dropout will help. But if we're using less number of parameters than are actually needed and we're still using dropout, do you think that helps, or has the literature says something?
Okay, so the question is, it is kind of clear that if you're over parameterizing a model and we start using dropout, it might help with regularization. But if you're under parameterized, then what happens? Then you're already in trouble because you've under parameterized your model. So you need to first get rid of that problem. So what usually you would do if you were trying to model some data is you would try to gradually increase the parameterization or the expressivity of your model until you start seeing overfitting, and then you start regularizing from there. So that is what you do. Yes.
Now, this doesn't give us any indication of which features we might be able to take out.
None. No. Yeah. Okay. All right. Not really needed. In this class, we'll basically now start looking at applications of how to build upon the feed-forward networks and do some real-life problems. A quick note on receptor fields is how you get the input is very important in a machine learning model. So for example, again, people try to mimic eyes for the longest time. And there are these rods and cones in the eye which light up based on different colors. But we still don't know how shapes are modeled in the eye. And it was a big challenge for computer science in general to try to model it. So basically the higher level idea is you're trying to, you want to model how, or you're trying to come up with ways to model the input data. So for example, they could just be, in cases of images, they could just be pixel values. So for example, if I give you this task of image classification, where I give you an image, and you have to come up with a network, a model, which tells you whether there's a face in the image or not. And okay, I tell you that all these images would be black and white. What would you do, given all the knowledge you have now? Yes?
Maybe reshape a bunch of images so they're all the same size, and then feed the pixels in as input parameters.
Okay, so that feed-forward network is just a depiction. It could be decision trees or whatever you want. Like, okay, so you said, take an image, reshape them to have the same size, and then you would?
Use the 0 to 255 pixel value as
okay.
Input.
Mm-hmm.
N by m of them depending on the pixel size.
All right.
Or the picture size.
Sure.
And then train a bunch of photos with faces, a bunch of photos that aren't faces.
What would you train?
So you would input a bunch of faces, so a bunch of
images, pixel values, and that would go into what?
Say that again.
What would that go into?
What would that into?
What would that go into, this vector that you've now created, the image? It would go into a feed-forward network?
That would be your feature space.
Okay. And what is the model you're using?
So I originally went with neural network, but you told me it could be anything.
Yes.
Okay, so cool.
Something.
Neural network, why not?
Okay. And then you would train.
So you have labels of 1, then you have a bunch of things that aren't faces, and you have labels of 0, and then you train your model.
Yeah. Did everybody get it? So the idea is basically take an image, which is say m cross m. So there are m squared values in this image. Each value is say between 0 to 255, a grayscale value. You vectorize it into this long vector of m squared values, and then you pass it onto a feed-forward network as deep as you want, and then you train it to do some classifications. Does anybody like this idea? Sorry. Why do you not like this idea? Yes? No, sorry. So imagine M is 10. So it's a 10 cross 10 image, which has, so, okay. So images are represented as pixels, right? They're discretized into these little boxes. And so let's say it's a 10 cross 10 image. So it has basically 100 values in it. Right? Okay. So M is not, but each value within it is a value between 0 to 255. Or you could normalize it to be between 0 and 1. That's really not the point. But yes, so any issues? Yes?
It's a lot of features, so we need to make it more. So we should use PCA or something.
Okay. Okay, so one of the issues we are told is that's a lot of features. And we can try to do some kind of dimensionality reduction. Okay, that's okay. That's the idea. Yes.
You're throwing away the spatial information, so you need to somehow use that because that's important to an image.
Right. Is that clear? Okay, let's go over it. So suppose I have 100 cross 100 sized images, and I make the first hidden layer to be of 1,000 dimensions. How many parameters do I have now in this one hidden layer? Sorry? 10 to the 4. No, a little more. Cross 1,000. So, okay, so our friend tells us the input image is first vectorized into a vector of size 100 cross 100, which is 10 to the 4, and then which is whatever M was in the first slide we saw today, and then you're going into a hidden layer, which is of 1,000 dimensions. So the parameters for this hidden layer would be 10 to the 3 times 10 to the 4 is 10 to the 7, a lot, right? This is 10 million parameters only in one hidden layer. Okay, then somebody told us we're losing out on spatial correlations, and that is the main issue with trying to create this receptive field, which is just a vector of pixel values for an image. What makes images are these spatial correlations between things, right? That there are two eyes next to each other, there's a nose in between them and a little below them. So those are very important to be captured. So feed-forward networks wouldn't really work in that case. There's an issue of variable-sized inputs, but suppose we downsample them to be of the same size or something. Yes?
This is maybe too general of a question, but say you have like a vertical green line, and if you were to vectorize it, you of course would lose the fact that it's a vertical line because it's all one line. You just get a bunch of 0, 0, 0, green, 0, 0, 0, right?
Sorry, I didn't get your question.
Yeah, so
you're trying to say that suppose we have an image, and within that image there's a green vertical green line.
Image with one pixel with green line going down. If
right.
you vectorize it, you'd lose the fact that it's a line, right?
Kind of, yes.
And,
not particularly true.
All right, because I was going to ask if you have sufficient expressivity that the whatever model you create would be able to recognize that every time you modulate over whatever M is, they happen to line up exactly. Is that something that can do?
Yes. In theory.
Okay.
Yeah. So basically the whole point was that if there's an image and there's a vertical green line in it, I claim that you are losing out on spatial information. But that is not really true because you kind of know that suppose the first column of that image is a green line and the rest of it is 0. You know that any pixel value you get in this vector modulo M, if that's 0, that's a green value. So you're not really losing out on spatial information. True. So in theory, feed-forward networks can model it. True. We saw that in the last class, there was this slide about representational capabilities of feed-forward networks. And we saw that a 3-layer neural network can mimic any function on this planet. So yes, in theory, you could do it. The issue becomes optimization. There exists a function that will be able to model it. The question is, are you able to find it? And that is all what we're dealing with. Great. Okay. Does that answer your question? Correct.
I think the point here is not that we're losing spatial correlations, is that we're modeling spatial correlations which are not exactly important. So we're also trying to model the first and the last pixel being correlated, right? And that's what we're trying to say, right? That we're over-parameterizing it to
kind of, but that correlation might be important, right? For some other task. So the point was that in this feed-forward network, you are kind of modeling these correlations, but maybe you're over-modeling them, that you're modeling pixels that you might not really need, but that is not the case because we might really need it for some other task. Maybe the task is the top left and the bottom right corners the same color or something. You never know. Anyway, any solutions that come to mind for this? Yes.
Is reducing the size of the hidden layer the wrong approach?
Kind of yes, because you're then losing out on expressivity. So it is obviously an approach to try, but I highly doubt that it would work. Any other ideas? Basically, what we're after is trying to model spatial correlations in images.
Instead of feeding the direct pixels, we could extract some other information and feed them.
And yeah, we all know that. But how is the question? So the idea is don't give in direct pixel values, but try to extract something out of it, and then give that as information. So this is precisely the idea of feature extraction. I don't know how much of that you've done in this class, but you're basically trying to extract some high-level features from this image. Okay, what are high-level features in an image? Edges, yes?
Yeah, you have like entropy of certain pixels.
You try to find entropy of 2 or more pixels. You try to find how do they change. But basically the idea is you try to find some kind of edges, you're trying to find some kind of shapes in the image. So basically some kind of local features. So what makes a face, for example, is that there are 2 eyes. So you can try to say, find an eye, and then you say, is there another eye in the vicinity of it where it should actually be in a human? And then is there a nose I can find, and is that nose between them, or something like that. So basically you're trying to find some smaller features in this image and then compose them into saying that does it make coherent sense later on. Okay, we don't really need to look at this. Okay, so this is the idea of convolution layers. So there's this neural network architecture, and what it tries to do is it argues that what I will make is small filters, where these filters will try to model some kind of these high-level features like edges and shapes, and then I will compose them. I will try to use this filter over the full image, and then compose it, and then try to do some classification later on. So these filters are basically just matrices, like parameterized matrices. So for example, you saw in feed-forward networks, you saw hidden layers, which are basically parameterized as matrices, like the W1s, 2s, and 3s. You do something similar over here. We will try to look at it, or we'll at least try to look at the intuition behind what is happening. Anyway, so one thing that you should take from this slide is that what you're going after is learning small matrices called filters that will try to find edges or certain shapes or certain features in images, and these filters will have trainable parameters in it. Basically, these are trainable matrices. And how those are used, we'll look at it now. Okay, how these filters are used is via this operation called convolution. Does anybody know what convolutions are? Is anybody from like an electrical engineering signal processing background? No? Okay. Anyway, convolutions are basically are compositions of functions. What they try to do is you take 2 functions and you try to model how the shape of them gets modified. again, on a very high level, if you have a function f, which will act as our filter later on, the small matrix, and you have a function g, which will later on act as the pixel values in the image. When you convolve this filter f with g, what you get is that weird hill shape, and it tells you that there is a rise in the values in g, and then there is a fall off. Do you get a very high level intuition? That is all you're looking for in studying this. Does that make sense? Okay. So this is a very high level idea of what is going to happen. So for example, you could have this very pixelated, unsharp image, and then you have a filter of size 3 cross 3. And what will happen is you will convolve this filter, and you will stride this filter all across the image, and you will get some outputs from it, and you will see what happens after that. So one filter operation, what it is doing is basically wherever you apply that 3 cross 3 filter on the image, you will multiply the values of that filter with the pixel values, and you will sum them up. And you output that, and you do a striding value. So it is shown that if you have a filter like that, does anybody see some symmetry in that filter? There is a certain structure in that filter, is that the diagonal value is positive, the off-diagonal values are negative. So when you have a filter like this, it precisely does something similar to this, where it tries to find these jumps in the pixel value. And usually edges have these sudden changes in color or intensity, and hence it is also called the sharpening kernel or the sharpening filter. So it tries to do this and sharpen these edges out. Do you get a high level intuition of what is happening? Okay, then yes?
I don't understand exactly what's going on here.
Okay. Okay, so let's start from bottom up. You're given an image, and you're after finding edges in that image, right? So there is this technique called convolutions, which tells you that for a given function, I can tell you a function which will tell you if there are sudden spikes in it. So given a function g, there is a filter f, and when you apply this convolution operation, somehow it tells you where are the spikes in this function g. Okay? So this is in 1 dimension. When you take this to 2 dimensions, this function f, in this case, is that matrix on the top, that 3 cross 3 matrix. And it tells you when I do this convolution operation in 2 dimensions, mathematically, however you do it, it will try to tell you when there are sudden spikes in pixel intensities. And pixel intensity spikes in images means that there are certain edges in that. Does it?
How are you applying it?
How is it applied? We don't really need to go into the details, but how it is applied is you have an image, the big one in the back. You have this filter, which is 3 cross 3, and you do this operation, which is you multiply the image pixel values to the filter values, and then you sum them up. So what you get here is you multiply that 3 cross 3 matrix with the image, and then you sum them up and get this one value. Okay? Then you shift this slightly. You again do this operation, and you get another value. Yes, yes.
Don't you end up with the same number of features?
No, we'll get to it. Sorry, 1 second. You also had, yes.
Like a discrete cosine transform, then the frequency of
Yes. So convolutions, for whoever knows it, it's basically a Fourier transform. Yeah. So yes, that is why signal. These ideas are basically coming from electrical engineering and signal processing spaces. Yes.
Does it matter if your filter guidance the path of image that is being convolved
maybe, maybe not. It depends on the application you're looking for. And yes, it basically depends on the application you're looking for. Yeah. And it could certainly do it. Any other questions? I'll come back to your question. Yes?
So in the previous slide on that image, so the two images are the same size. Oh, so it just makes the outside just black? How does it handle those that are like edge pixels where there's no, obviously like half the matrix is missing?
Yes, but also take this particular image with a grain of salt. Yeah. Yeah, don't read too much into it. Yeah. Okay. So all in all, what you're doing is you have this trainable filter. You would basically stride over the image and apply this using some mathematical operation, get these values out as this little blue matrix over here. Okay. Now there was a question that after we do this convolution operation, do we get the same number of features as the number of features in the image? Does anybody want to answer that question for us? Yes?
So in one of the dimensions, if the input image feature size is f,
Mm-hmm.
and the kernel size is k, then the final output would be f minus k plus 1.
Would it be more or less?
Less.
Less. Okay, so it would be less, right? Because you don't, so here when you see, I would start here and I would only be able to go a certain depth down, right? So hence, you're getting the output features or whatever the output is of a smaller size.
Are you just losing the border?
Kind of, but you've also used it in some sense. But there are techniques to do it. Exactly. So the question is, are we losing out on information at the borders? And the answer is yes in this case. But what people usually do is take an image and put some zeros around it, and then start the convolutions outside the image. So that this 3 cross 3, the lowermost row, is actually the first row in the image, and two of them are actually working on zeros. Just to tell you that, oh, there's an edge in the image. This is where the image starts, and you would do it, and you would get the output of the same size as the image.
Right.
Okay.
So in that case, you would in fact get the same size.
Exactly, yes.
Can you explain again how are the dimensions reducing?
Yes. So, okay. So what is the size of the image in this case? The original image? It's a 6 cross 6 image. All right. I start from the top left corner with a filter of size 3 cross 3. So what is the lowermost edge of the filter? What is the location of that point? 3, 0, or in computer science 2, 0. And then you would go down 1, right? So you would reach 3, 0, 4, 0, and 5, 0. So how many convolutions are you able to do when you go from top to down? 4 from 2, 0, 3, 0, 4, 0, and 5, 0, right? So that is what you see in the output. Does it make sense? Right? And similarly on the XY axis, right? So this is the maximum you can go to, right? So you'll only get 4 values in that dimension as well. And hence, the output you're getting in this particular case is a 4 by 4 output. Okay, yes?
So you're only eliminating a constant value of pixels, essentially. Like someone else said, the border.
Yes. Yeah, precisely correct. Yeah. So, and also somebody alluded that suppose the image is of size m cross m, and the filter is of size f cross f, the output will be m minus f times m minus f plus minus 1 here and there. So it's a constant number, yes. And you're getting rid of the edges, but not really important. People pad zeros around it and still get an m cross m image out or something.
So I mean, learning the polygon interface is just another learning problem. I mean, you're basically trying to take the features learn, I mean, the original pixels, learn the polygons, then feed that to the neural network, right?
Exactly, yes. We're after a learning problem. What we're after is, people have tried it. We didn't look at it here in detail. People tried to actually use feed-forward networks, just give out pixel values and try to learn deep feed-forward networks, but it wasn't really working out. You kind of know in theory that it should work out, but it does not. And then people try to come up with these different architectures to help the model. Do we remember in the last class we saw this demo of this weird spiral shape we were trying to classify? We give it x1 and x2 as the only features and a very deep model, and it did learn it, but it took a long time. And as soon as we introduced x1 squared and x2 squared features, it learned it in a much faster manner. So giving input in the right manner still helps. And
So is that an example of convolution?
not really. I'm just trying to tell you that better input spaces will lead to faster and probably better learning. Yeah, so that is all we're after. We know that edges and shapes matter when we look at images. So that is the kind of, it's called inducing a bias in the model, or it's called giving the model an inductive bias. That is all we're after, is giving a bias to the model to care about shapes and edges. And it has shown to really help in learning. Okay, so you do this convolution operation, you fill this matrix out. Can anybody tell us what the size of this of the parameters are that we're looking after in this convolution layer? Yes? Just 9 parameters, the 3x3 filter parameters we had. Is that clear? Okay. All right, making a black box out of it. So you get an image, a blue image. You have this convolution layer, which basically has a filter in it. You apply this convolution, you convolve this filter with the original image, like you're doing here, and you get this matrix out, which is shown in red over here. Okay, what you can also do is have multiple filters, not just one, which could be of different sizes as well. You could apply them and get multiple outputs. And what you could also have is multiple channels in an image. So usually a color image is represented as 3 primary colors, the R, G, and B, red, green, and blue. So you would have, instead of 1, but 3 matrices, so you can do the same filtering operation on all 3 images. So you will basically get a bunch of output from these convolution layers. Is that clear? Okay, then what you do? Then what you do is this operation called pooling, which is, again, proven to be very beneficial in trying to model images, is basically what you do is take a local patch of an image, and you pool the values into a single value. There are many justifications and reasons for doing that. We'll not really be able to go into those. But the idea is basically to pool a lot of these values from a local patch into a single one, like this. One of the operations which is very commonly used is called max pooling. So what you do is you take a local patch, say again a 2x2 patch, and you take whatever the maximum value from it is, and you just store that, right? This is another way of reducing features. So somebody in the class mentioned that you could use some kind of a dimensionality reduction, a PCA. In images, after doing a convolution operation, it is shown that max pooling really helps, and you don't need very expansive methods as PCA to reduce dimensions. So you do max pooling like this. There can be multiple max pooling or pooling layers or methods to do pooling, and you will get some output out. So this is technically one layer of convolutions you've done. Again, so what you do is take an image, run the filters, get these outputs, you do some pooling, and you get a smaller output out with the dimensions returned. This is one layer. analogous to one hidden layer in a feed-forward network. What you would usually do is connect a lot of them serially and then get some output. Then if you're looking for doing, say, binary classification, what you could do is then vectorize this matrix you get and pass it through a feed-forward network and do some kind of binary classification or multi-classification that you're after. Okay? Any questions? Okay, great. Some high-level architecture of what you could do. Given an image, you get these multiple feature maps from different filters and convolutions you did. You do some pooling to get these smaller outputs. You again do some convolutions. You do, again, some pooling. Then you vectorize it out, do some feed-forward layers, and get whatever prediction you wanted out. Okay. Yes?
So isn't that like a ton of features now?
Yes. Ton of features, yes.
Doesn't that kind of stray from our initial goal?
Yes and no. So our initial goal, our only goal is basically to make a good model, right? Then we saw that over-parameterization might hurt. So if you actually look at convolution layers, it is actually very less parameters because you have a filter and you use the same filter across the full image instead of introducing a new weight value from each pixel, right?
So the final model is going to see less, but in order to reduce it, you do a whole massive featurization.
Right. So you're getting a lot of hidden outputs out, but the parameters that you have to learn are actually usually lesser, until and unless you make thousands of these layers. Yes. But actually, the biggest issue has not just been over-parameterization, but it has actually been inductive biases. How do you actually make the model see what are important correlations? And this helps. Okay. A quick note and a very high-level one on. So what we've still done is just a bunch of matrix multiplications, right? We might have done them in a crazy order, but we've just done matrix multiplications, which are differentiable. So you could still use the backpropagation algorithm we learned in the last class to train this model. Is that obvious? Hopefully it is. That is one very important nature of neural networks is as long as you're making differentiable outputs, it is trainable in some way, right? So again, you would get some error at the end. You would compute some gradients from the last layer, use them to compute some gradients in the layers before that, and you could still do this backpropagation. Even though this architecture looks crazy, it is differentiable because it is composed of continuous differentiable functions. Okay. These are real outputs from a model. So this does not correspond to one image. These are just stacked up to show what different layers were learning. So you would see that the initial layers, the filters there, were learning these edges. And then what happened was the later layers were able to use the output from there, which would basically be telling where the edges are in the image, and then compose them to form these different shapes. So you would see lines, circles, right angles, and all sorts of weird shapes, or basically parts of shapes. And then the layers after that, what they were able to do is compose these parts of shapes or small shapes into larger objects. So on the bottom left, you see some kind of a hive structure and a bird, and there's a wheel on top somewhere. So it does really work in a way that we're looking for. Yes?
So what's being printed out here? Is this the weight vectors at stage 1, or the weight vectors times x, but only on stage 1?
It's actually a little involved. This is the paper that actually tells what it is and justify why looking at it is important. But let's not get into that here. I can put the full paper name when I upload the slides. I saw, yeah.
So it seems like you make a difference between the
The feed-forward, yes.
Okay, so the difference between proposed convolutions and a neural net is a neural net, is it
Sorry, correction. It is still a neural net.
Okay.
I think what you mean is a feed-forward network. Okay, yes.
So the composed convoluted functions, is the difference that in the feed-forward neural net, you don't really define functions, it's just, you're just using the loss back propagation to change the weights, whereas convolutions you kind of are just defining them. Is that?
No, so let me reiterate. In a feed-forward network and in a convolution network, the difference is the functions that you use to get the output. In a feed-forward network, you were doing a simple matrix multiplication and then a sigmoid function over it. Whereas in a convolution network, actually, can somebody tell us what do you do in a convolution network? Quickly, perhaps? Yes?
Like you convolve the functions together with a filter to decrease the features.
Yes. Okay, let's draw an analogy with the feed-forward network. So in a feed-forward network, you had a matrix as a parameter, and you did a simple matrix multiplication. In a convolution network, you had a matrix as a parameter, which was the filter, but instead of doing just a simple multiplication, you did this crazy striding multiplication, and then you did this pooling, and then you got a vector output. So it is only in the function space how you're actually doing the functions. The back propagation still remains the same. You would still compute errors in both cases and compute gradients and do a step. I hope that clears things. Okay.
Your error the gradient will be computed with the final vector which comes out after the convolution.
Yes.
And how would it affect the update? It would affect the update of the convolution filters values.
Right. So the chain rules and whatever we looked at the last time, right? As long as the output is a function of everything in between, you would be able to compute a gradient for everything in between. Okay. You don't really need this. Quick note. This really small thing is actually the kind of networks we use. People use these days. It's crazy big, bunch of layers, but it kind of works. So this is a graph. So there was this ImageNet data set, which was basically a bunch of images, which were of different objects, and the task was to classify what image had what object in it. So before 2012, so the convolution layers were actually introduced in the 1980s, but people struggled for the longest time to train them because our CPUs weren't good enough. We didn't exactly have the optimization tricks we needed to solve them. And you would see that the error rate was around 28, 25% at the time. 2012, people figured out how to use convolution networks to model images, and you see this sudden drop in error rate, and it has hence been just going down. So that area is also, that time around 2010, 2012 is also called, is also known as this revival of deep learning, because there were these bunch of different tasks in computer vision, which deals with images, in the speech community, and also in the natural language processing community, where all these architectures now started to help us a lot. And it was a great switching point of things. Okay, let's switch gears. Any questions? Any questions at this point? Yes.
Max pooling, it is not differentiable, right?
Yes.
So how can I execute it?
Great question. Can anybody? So the question is, or the comment is that max pooling is not differentiable. Why is that, and how do you deal with that? Mm-hmm.
To deal with that, I mean.
No, why is that? You first agree to the problem, then try to solve it.
It's non-continuous.
Yes. So does everybody see that? So max function is non-continuous. It basically seals out. If I give you a function, or I give you a bunch of, say, I give you 4 functions, and I just tell you what the max is, you don't know how much changing the input would actually change this max value. because it might happen that the max remains the same. So there is really no gradient. You might be changing the input, you would still see no change in the output. So the gradient at a lot of times would be 0. So yes, it is not differentiable, but how do you deal with that?
Actually, it is continuous if the four functions are continuous, but yeah, you have kinks.
Yes.
But so what you can do to deal is, so if the max value must be one of the four values, so you can just backprop that to the one which was the max, and you can just leave the rest three alone.
Yes. So that is exactly what happens. So imagine you had 4 ways to get to the output. But what you did was take the max of them, and then you reach the output. You would still have one path to the input, right? And you would only update that. So yes, in a convolution layer with max pooling, not all weights get updated at all times, but it has been found that even this sparsity in gradient updates doesn't really affect things, and it is able to train. That's a very good point. Yes. Any other questions?
How do you choose the size of the
Again, it's not just about convolution networks, but about machine learning in general. You start small with small filters, small number of parameters. You usually see that your model is not doing good. You try to increase it. You try to increase the expressivity of the model until you start seeing that it starts overfitting on the training data, that it is at least able to model the training data well. You might see generalization issues where your test loss or your test accuracy is low. And at that point, you try to either reduce the parameters or regularize the model depending on what is happening. Yes, it's very hand-wavy. Yes?
What if you have features of different sizes in the image? You need filters of different sizes, and so is it possible to use different size kernels and then stack those?
Okay, so the question is, what if the images are of different sizes, right? So there are multiple solutions. First of all, you can try to downsample images.
I mean the features in the image. So you have small circles, but then you have larger circles of larger radius within that one image.
Right, okay, so we didn't really go into that, but this convolution layers, or this convolution operation, or this convolution layers are actually made to deal with that. And it has shown that they are size invariant and they are rotational invariant. It is hard to see that. It would take another hour to see, but you'll have to take my word for it. But yes, convolution networks are precisely made to do that. So suppose if I train a model on a bunch of images where the faces were upright, and then I flip the test images, you might hope that the performance of the model will not be able to recognize it, but convolution networks are able to deal with it. Not 100%, but to a great extent as compared to any other architecture. Yes.
For it to be size invariant, you need to rely on the fact that it's deep, right? The network is deep. If it's not deep, still it's size invariant?
We don't know, but shouldn't be the case. All right, let's go ahead. I have tons of slides. We'll not be able to do it, but let's see. A quick application in natural language processing. So suppose you have a task in which you're given a sentence, and you have to find the parts of speech tags for each of the words in the sentence. And you're looking for a neural network architecture to do it. Can anybody quickly try to tell us what are the challenges in trying to model something like this with whatever we have seen till now? Or what are the challenges in general in trying to solve this problem?
Sparsity is one challenge. So
yes, okay.
then the input feature size is large, so the dictionary is actually a large thing.
Okay.
Location of words in the sentence.
Right. I just realized there are tons of challenges to go over. But okay, so the high level ones are, first of all, there are a lot of words in the world. Then the other thing that makes it unique, there are much more images in the world, I believe. But one of the other problems is that there is this dependence on on what is to the left and right of a certain word, because if you jumble up this sentence, it won't really make sense. So you have to model that. Then one of the other issues is there is also some dependence or correlations between the outputs. So you would usually see nouns after determiners in a sentence. So having that knowledge or a model trying to understand that knowledge and using it would also help. So these are the kind of inductive biases we're looking to bake into the model. And then there is this very important big challenge in natural language processing is of ambiguity. So for example, these two sentences contain the word saw in them, but in one of the sentences, it's a verb, and in the other one, it's a noun. So you know that if you were to just output parts of speech tags by just looking at the word, you will make errors. So you'd need to look at the local context, the words around a certain word, to be able to make predictions in a good manner. Can we use feed-forward networks to model this problem? And if yes, how? And if no, why?
No, since the input is variable.
Okay. Okay. So good enough reason. These sentences can be of different lengths, right? So even if you were to vectorize a sentence somehow, you don't know how to use feed-forward networks because these sentence lengths will be differing. I'll have to quickly go over this. Okay. So what people came out with was recurrent neural networks, where what you do is you have some function with parameters w, and you apply it, say, only to the first token, the first word in the sentence, and you get some hidden outputs, some h0 in this case. This function could be, say, a feed-forward network, where you somehow vectorize the word. You get a vector for a word. You multiply this with a weight matrix, and you get some hidden outputs. Then what you do is you take the next word, and this next word, but also take the vector you produced in the previous time step, and you use these two vectors now to come up with a new vector, say h1. And the idea is that this x1 is telling you what the second word is, and the h0 vector is telling you what the previous history is, or what are the words that I've looked at before. And then you get some h1 output. Quick note, this function in between that you're doing is still the same. So like you were reusing the filter in a convolution layer, you're using these parameters here. These are not new parameters. And hence, you're able to deal with variable inputs, because now I don't care of how long this input is. I will just keep doing this in a recurrent manner. Is that clear? Any questions? No, great, okay. So, an RNN, what it does, it basically takes a vector as input at every time step, that is from the input. So for example, in natural language processing, it could be some vectors corresponding to a word. It would take some hidden vector from the previous state, which tries to capture some kind of memory of what has been looked at before, and then comes up with a new vector. So at, say, time step t, you get x sub t minus 1 and h sub t minus 1 as two inputs. You do some function, and you get ht as an output, and you keep doing this. Yes?
So the ht or the ht, usually the first word is a noun pronoun. Is it something like that?
For example, if you were training to do POS tagging, you would hope that these hidden vectors try to model what the words before were, or what the POS tags I've created before were, or depending on the problem, it could change. Right? Suppose if you were training this model to output a number which was just 1 plus before the previous number, then you would expect ht minus 1 to just have that information, and it doesn't really care about the distant past. Okay? All right. Okay, a very simple function you could use is basically just two simple feed-forward networks. You take the input at any time step t xt, you pass it through a feed-forward network with parameters, say wi, and you take the hidden vector ht minus 1, you pass it through another feed-forward network, you get 2 vectors out, and you just add them up. And maybe you do a nonlinearity or something, and that is your ht. So again, what we have as parameters now is just 2 matrices, right? But you have the capability of modeling infinite length sequences. Is that clear? Okay. Don't think we need to go into this. Okay, quick note here. It might be a little overwhelming, but you could see RNNs, or these recurrent neural networks, as just unfolded feed-forward networks. Let's try to quickly look at that. Basically, the whole idea I'm trying to impart is that you can still use back propagation. Because at the end of the day, what you're doing is just applying compositions of functions where these functions are continuous differentiable functions. So imagine you have these 3 inputs, 1, 2, and 3, and they depend on each other in this crazy manner. So at time step 0, what would happen is 1 would tell 2 its value using this function w1, or w2. 2 will tell its value to 1 using this function w1, similarly, and you get to time step 1, right? You would keep doing this operation, and this should look like a feed-forward network to you. Any strict reservations against that? Or just take my word for it now. Yes?
How do we get the 2 to 1 thing?
This is, I'm not talking about a simple RNN. I'm just saying, imagine there's a model in which you can output 2 to 1 using this function w1. Yeah. Anyway, we only have a minute left. What are we doing? Probably last quick note. The RNNs we looked at in the last 5 minutes only look at text in a left to right manner. And it might be important to also look at what is ahead in the text. Maybe the sentence ends, there's a quotation mark that starts, or anything. So people have come up with bidirectional RNNs, where you basically take 2 RNNs. One goes from left to right in a sentence, the other one goes from right to left. And you can, at every time step, what you would get output is hidden vectors, so 2 of them, and you can again compose them into a different hidden vector. So it's basically a playground. As long as you're coming up with continuous differentiable functions, your network is trainable. It might not train, but it is trainable in theory. Okay, I think that is all. There are a few slides left. I'll put it up on the website. If you have any questions, you can email me or ask any of your post support staff. All right, great. Thank you.
To find the gradients with respect to W for an RNN, what you
With
can
respect to?
RNN, W. So suppose that W is just a box. You can assume box, as you said, the weights. So one thing you can do is, so you can just assume that for every input, you are using some different W1, W2, W3. You can just find the gradients with respect to all of them and just add them up, right? That's fine. That's how it works, right?
Find the gradient of a W5 or say a W3, you will need to know the gradients of W5.
And they are the same. Oh, so this.
Yes, so basically, internally that is what happens. Is you get gradients at every time step, but you know they are the gradients for the same parameter, you just add them up. That is exactly what happens.
They just add them up, okay.
If you work it out mathematically, that is what it comes out.
Okay.
Because in a chain rule, we saw that if there are multiple paths to get to the same output, you're basically adding them up.
Okay.
That is exactly what happens.
Thanks.
Yeah. Go on. quickly get up.
In,
Was it a rant? Like, I need to honestly buy a new one. Because I didn't
Do you also have
like, I have had a, yes, you backed me up. That I think it's fit.
Suppose there is this huge map from word to vector. So there is a word in this, and there is a vector, and then there is a word saw, there is a word new, and there is a vector. So what I would first do is look up these vectors. So suppose these are vectors I, j, and k. So my x1 is actually equal to this vector 1.
V1
P1
is just the first.
just the vector corresponding to this word I.
So x2 is the vector corresponding to solve.
So x2 is equal to, yes, the vector corresponding to the word saw, and x3 is the vector corresponding here. Usually what you do is h0, you just input a vector of 0. You take x1, you take x0, and you produce h1. Okay? And then you take this x2 vector and h1, and you produce some h3.
Why would we want the output of V1 like H1? Why do we need H1? Is it feedback? Like, how does it help the
Okay, so let's look at this token saw,
okay.
and we're trying to find what is the part of speech tag for this word saw. For example, there are two options. It could either be a noun or it could be a verb. Okay, so suppose I write this sentence, a saw
So it,
versus I saw. So the information of the preceding word is very important in telling you what the part of speech tag of this is. So suppose, so you would expect that this h1,
is a noun. So I
not really, it just contains some information that this is the vector I saw before. And then you expect that this to use this information and this information together and say that, oh, this should be a verb because I saw I before. And I know that I is a noun or a proper noun. Similarly, if I saw you would say that, oh, I saw the word before, which is a determiner. So this is probably a noun rather than a verb. Does that make sense?
thank you.
Okay, I have a question with INNs too.
Mm-hmm.
You showed that image where a recurrent neural net is probably like a feed forward net,
Yes.
but you have these repeating weight vectors.
Mm-hmm.
So when you're doing backpropagation, that means that you have to update all of the vectors in one go. Does that mean you actually do backpropagation through all the layers, or do you just do one? Because how does that work?
Okay, so first of all, let's look at what is a layer. So this function here has say parameters w.
Yeah.
This also has the same parameters.
Yeah.
Okay. Suppose you have a third token, I saw you, and there is another the same parameters. What you get is say the y at the end that we are looking at in the feedforward network, and there is a truth t. Okay? You compute some error function of y and t, right? This becomes some loss value, some scalar, right? Just a real number. You compute gradients. What you would get is some gradient of w, but at time step 3. You would also get a gradient of w at time step 2, and you would also get a gradient of w at time step 1. If you actually work out the math, you would find that the final gradient of w is actually just the sum of these gradients. So this just becomes the sum of gradients of w at any time step. So it basically becomes similar to we saw parallel paths in a feedforward network, and the gradients will add up. It kind of becomes something like that. Alright, no worries.
Well, I have a question about, I'm just kidding.
I have a question, what's for lunch? Sorry, there was